In this video, we shall look at a few review problems associated with static equilibrium. First, a brief introduction. When a system is in the state of static equilibrium, two things remain true. The first is the net force on the system is zero. So that's condition 1 of static equilibrium. The second condition is the net torque acting on the system about any point is also zero. So this is the second condition. Let's look at the first problem. A uniform rod, that's this one right there, with mass 1.2 kg is hinged to a wall at a lower end. So that is the hinge. Its upper end is held in place by a rope also attached to the wall. If theta is 58 degrees, theta is the angle between the rod and the wall, find the value for the angle alpha so that the tension in the rope is 6 newtons. What is the force on the rod from that hinge? The first step is to set up the free body diagram of the rod. So it is the rod which is in a state of static equilibrium. The first force is of course its weight, which acts in the middle of the rod. And we know it is 1.2 times gravitational acceleration. The second is of course tension in the rope. Let's call that T. And we know what the value of T is. It's 6 newtons. And then you also have the force from the hinge at the lower end. Now we can divide that force into two components. The first one is the x component. Let's call it Fx. And the y component, let's call it F sub y. Now let's write down condition 1 for static equilibrium. Condition 1 is the net force acting on this rod is 0. Now this is a two-dimensional system. So let's define x-axis like that and y-axis as the axis that is going up. So let's set the net force along the x component to 0. How many forces are there that's acting along the x direction? One is this force, and the second is the horizontal component of that tension. So we can immediately set F sub x equals the horizontal component of that tension. Let's call it Tx. But Tx is 6 newtons cosine of that angle. And what is this angle? That is just 90 minus alpha. So you get F sub x equals 6 cosine 90 minus alpha, which is just 6 sine alpha. So there we have it. Equation 1. Fx equals to 6 sine alpha. Now let's do the same for the y component. How many forces are there? There is this F sub y which is pointing up, the weight 1.2 g pointing down, and the y component of the tension which is also pointing up. So we can write F sub y plus the y component of the tension, both of which are pointing up, equals the weight which is 1.2 g. We don't know what Fy is, but T sub y, or the y component of the tension, is 6 times, it's going that way, T sub y, so it is 6 times cosine of this angle, which is alpha, so it's 6 cosine alpha. And that is equation 2. Now let's apply condition 2 of static equilibrium, which says the net torque evaluated about any point on that rod is 0. Now we shall choose this point to evaluate the torque, because in doing so we will get an equation that will not contain F sub y or F sub x, which are themselves variables to be solved. So let's do that. So the first contribution to the torque about that point is from the weight. So torque is computed as the force that's contributing to the torque, so in this case it's the weight, times the distance from the axis to where the force acts, so that means it's this distance right there, and that is just half of the rod length. Let's call it L. So half of the rod length is L and the other half is L, times the sine of the following angle, the angle between the moment arm that's going in that direction and the force that's going in that direction. So it's that angle. From the diagram, this is theta, so this one has got to be 180 minus theta. So since theta is 58, 180 minus 58 is 122, so sine 122 degrees. What about the direction of this torque due to that 1.2 g? When you make a cross product of two vectors, so that is the moment arm for the torque due to 1.2 g, because it's going like that, the force itself is vertically downward. So if you take the cross product using your right hand rule from R to 1.2 g, your thumb will be pointing into the board. So the direction of the torque due to 1.2 g is into the board. The next term is torque due to that tension. So that's going to be the tension, which is 6 newtons. The distance from the axis of a rotation, which is here, is the entire length, which is 2L. So 6 times 2L times sine of the angle between the moment arm, which is going in that direction, and the tension, which is going in this direction. So the angle is that angle. So what is that angle? It is 180 degrees minus this angle, which we know is 32 degrees. Why is it 32? Because this angle right there is 90 minus theta, which is 58 degrees, so it's 32 degrees, plus 90 minus alpha. So it is sine 58 plus alpha. The direction of the torque due to 6 Newton tension is, according to the right-hand rule, coming out of the board. So this term is minus, this term is plus, and together they sum up to 0. Or you can just equate them. Now you see that L goes away, and you can solve for alpha. As an approximation, let's take G to be 10. So the left-hand side is 12, so that 12 will cancel this 12 right there. And immediately when you compare the 122 degrees to 58 plus alpha, alpha turns out to be 64 degrees. So alpha is 64 degrees. Now we can determine f sub x and f sub y. Fx is 6 times sine 64 degrees, which is 5.4 newtons approximately. And likewise f sub y, from equation 2, using g equals to 10, you will get f sub y to be about 9.4 newtons. So the magnitude of the force on the rod from the hinge can be determined using the following equation, like that, using f sub y and f sub x that we have computed. And if you do that, you get about 10.8 Newton of force. That is the hinge exerting on the rod. That solves the problem. Problem 2. A uniform ladder is resting against a frictionless wall. It weighs 210 newtons. A 45 Newton force is exerted at a distance L equals to 2 meters from the base measured along the ladder, and it's exerted on the ladder. Find the force due to the ground on the ladder. Express your answer in unit vector notation. So let's do all the forces. Let's list them out, a sort of a free body diagram for the ladder. The first one is, of course, the weight that's heading downward like that, and we know it's 210 newtons. That's given. The second force is the force on the ladder from the frictionless wall. That's going to go like that, 90 degrees to the wall. Let's call it F sub W. And the other two forces are from the floor on the ladder. There are two components. One is the X component. Let's call it F horizontal. And the vertical component, we can call it F vertical. Now let's write down condition 1 of static equilibrium. Let's balance the X component of the forces that's acting on the ladder. There are three of them. One is F sub H, F sub W, and 45. So the force heading leftward is F sub W, must be balanced by all the forces heading rightward, which is 45 newtons and F sub H. Now let's balance the Y forces. There are only two. One is the weight and the other one is the vertical force from the floor. So that would immediately give us the vertical component of the force from the floor. That's being 210 newtons, the same as the weight. Now condition 2 of static equilibrium, namely we want to balance all the torque. We can choose that point to compute the torque. So if we do so, F sub H and F sub V will not show up in the equation. We will only have three terms: the torque due to 45 newtons, the torque due to the weight 210 newtons, and the torque due to F sub W, which is the force on the ladder from the wall. So let's calculate the first term, the torque due to 45 newtons. So the force is 45. The distance from the axis of rotation is L, and we know L to be 2 meters. The angle between that force and the moment arm is that angle, and that is, let's call it theta. So sine of theta is just 8 over 10. So 8 over 10. Because we have a right angle triangle, this is 6, this is 8, this is 10, and that is theta. Note the force 45 Newton is heading to the right. The moment arm is going like that. So when you curl your fingers from moment arm to the force, your right hand fingers that is, the thumb is pointing into the board. So the direction of that torque is into the board. Now let's calculate the torque due to the weight. The weight is heading this way, so that is 210. The distance from the axis of rotation to where the weight acts is half the ladder length, and that is 5 meters. The direction of that moment arm is along the ladder like that, and the angle is that angle. So sine of that angle is sine 90 plus theta. Theta is the angle between the floor and the ladder. So sine of 90 plus theta is just cosine theta. Cosine theta is 6 over 10. So it goes there. The direction of the torque, according to the right hand rule, is also going into the board. Now finally the torque due to that force from the wall. So it's given by the force from the wall, which we don't know, times the distance from the axis of rotation, the entire length of the ladder, which is 10, and the angle between that force and the moment arm, which is going like that, is this entire angle right there, which is just 180 minus theta, because this is theta and that is theta as well. So sine 180 minus theta is sine theta, which is 8 over 10. So that goes into multiplying that term. The direction of the torque due to that force is coming out of the board. So that is coming out of the board. You see that this could be the minus term and this one has got to be a plus term. When you add all them up, you get 0 and you can solve for F sub W. Namely, this plus this equals that. When you solve for FW, you get about 88 newtons. Substituting 88 in here, you can solve for F sub H, which will turn out to be 43 newtons. And now we have the answer for both. And this is the answer in I hat J hat notation. Thanks for watching.